Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're going to take a look at how do we power things in space. So let's dive right into it. Before we understand that, we have to understand why there is a need for power in space. First, this power, whatever source we're going to choose, must provide power for the purpose, as in a geostationary satellite have a different power requirement than a spy satellite. So there are many criteria that must be met based on the purpose of the satellite. Many times spy satellites specifically don't want to use solar panels because that make them very easy to spot and detect. So they may want to use RTG to make a smaller footprint. And Soviet Union flat out used a nuclear reactor to do for this purpose. Then if you want to put humans in space, like in this, the only permanent installation in space for humans, you have to make sure the life support systems are working, because in space there is no buffer. The sole reason you can survive on Earth without needing power 24/7 is because there is a buffer which we call atmosphere that maintains it maintains everything. It maintains your body pressure, it makes sure you have a blood pressure, it makes sure your nitrogen dissolved in your blood does not go out of you. It also maintains the temperature. So suffice to say, even if you can create a very big station that has proper air air pressure, over time it's going to get either too cold or too hot. To maintain that, we need power. So it's a life support necessity that if you're going to put people in space, you have to make sure that there is a adequate power source that can provide enough power 24/7. So what are the criteria that we have specifically for space? First is power density, as in how much volume it's gonna take in your rocket to provide how much power. As in, like, let's say you have 100 liters of solar panel folded, obviously, so you have 100 liter of volume and it gives you out, let's say, 10 kilowatt of power, so it's good. Now you have 100 liters of RTG, it only gives out 50. So you have to make a decision based on power density. Then it also comes to the fact that how easy it is to use. Let's say you are building a simple communication satellite. You don't want to invest time in building nuclear reactor or building RTGs or figuring out some other things. You just want ease of use. For that reason, you're gonna pay specifically close attention to ease of use, how easy it is to use, because everything adds up to the cost. So if it's hard to use, you're gonna have a tendency to not favor it. Then we come to robustness. This is very crucial. So as many of you know, if you have something extended out like this, your arms, and you did that in a rocket launch, this is gonna break apart. So robustness also plays a crucial role. And not only that, like while launch, it also plays a crucial role while you are in orbit. Let's say many of the satellites do what's called maneuvers, and the maneuvers can be high G maneuvers. For that reason, they have to make sure that it classifies for robustness, as in it can handle that G loads that you're gonna impart on it. And final but not the least is how long it's gonna work, because satellites are so expensive. Nobody wants to put satellite that's gonna fall off the sky for, let's say, 4 to 10 hours or 1 day or 20 days. So they want to make sure how long it's gonna last. They know it beforehand, so they can decide whether they want to spend money or not. Because let's say your satellite works for 5 years, so you have to make sure you get the cost of it at least in first 2 years. Because if you don't get the cost of the satellite back, you're not going to make any profit. If, let's say, it spends so long, let's say 4 years to make the cost back, you have only 1 year of power left, you are in a loss because you're not going to make a lot of profit. So longevity also plays a very crucial role, especially for satellites. Then we come to some options that we have. First, we have solar. Now it's very simple DC power. You don't have to worry about it. There is no moving part, there is nothing that can go wrong. It's very simple, elegant, and it has a lot of power, like very idiotically large amount of power, as in like you can make megawatts and megawatts of scale, megawatts of solar panels. So suffice to say, it has a lot of power. However, the crucial aspect of it is that it's range limited, as in it's almost like electric cars. You can't go very far, as in the furthest we have sent on solar power is Jupiter, and if you want to use these solar panels on Pluto, they're not going to give you any power. And the sole reason this is even possible is not that solar panels have become magically 10 times more efficient. They are efficient, much more efficient than solar panel used in International Space Station. However, the sole reason this was even possible is because the advancement in mobile technology, basically processors that consume very little power, data transmission that consumes very little power. So all things combined, this was possible. Now be mindful, this is pushing it. Like even while this project was greenlit, there was a concern that this might not be enough. Like they might send the power and minor things would happen and they may not have enough power. So suffice to say, there is a severe range limitation, and that happens inherently to every star. It's not like if you had a brighter star, of course you can go further, but then again there would be a limitation where you can't go any further than that. It's inverse square law. Basically, the further you go, the lower energy you get, even in space. It does not need an atmosphere for that. So you can have the power powering your space station in moon orbit, like LOPG. I have made a video on that, deep space gateway basically. So you can have solar panels there, but if you want to put a human habitat, let's say near Jupiter, yeah, you can't do that. It's very low power. So you have to be mindful. Solar is very range limited, so don't design a concept art where you have solar panels going into interstellar voids. Then we come to solar thermal. Now the reason why you want to consider solar thermal, like these sort of thing, rather than solar panels, yes, of course this does have inherent side effect of having moving parts, as in there is more things to physically break, but it does use more of the radiation available. Let's say sun is giving out 100 watts of power. The 100 watts of power is not uniform in optical spectrum. A lot of power is in X-ray, a lot of power is in gamma rays, which you can't use. So let's come down anything below that. A lot of power is in microwave, a lot of power is infrared. Our sun is specifically very bright in infrared. So your solar cells flat out ignore them. Like they try to utilize them, but they can't utilize it to its max potential. But if you use solar thermal, it uses all of it. Especially in space. In Earth, there is a problem because of our atmosphere. It gets scattered and some of the spectrum is flat out blocked. In space, you're gonna get a lot more power. Like let's say sun is giving you 100 watts of power per square meter, you're gonna get, let's say 90 watts per meter square. However, if you use solar cell, you will be lucky if you get even 50. So for that reason, for optimum utilization of the power that is already there, this plays a very crucial role, and it gives you a lot of AC power. Like the power is AC, so let's say you build a very big structure and transmitting power from one place to another becomes a hassle. It does provide AC current. Then it is cheap per megawatt, as in like let's say you want to build next generation International Space Station, which is gonna have 10 megawatt of power requirement. Yeah, solar cell at that point would be very expensive. This starts to become cheap at that scale. The bigger you make, the cheaper this gets, because the only thing you are gonna add is mirrors, and then all you need to worry about is Stirling engine. You're gonna have 1 or 2 Stirling engine in backup, and one would be running. So, but this also suffers the same problem as limited range. You can't put this in Jupiter. Of course, this will work better than solar panels, but still it has a range limitation. And this concept is a very interesting concept. I will put the link below, and not to mention I made a video about that here also, where you can see how we can use this sort of structure to provide power, entire power of planet Earth. So space solar power. Now we come to the RTGs. This is the sweetheart of space industry, simply because this is ludicrously long lasting. Imagine a battery, normal battery, you just put in and you forget about it. For how long, you may ask? 10 years, 20 years, 30 years, 40 years, it's possible. Like 30 years has already been achieved. 40 years it's doable very easily. 50 years kind of pushing it, because not because the battery itself breaks, other things starts to break. Let's say your microprocessor starts to break, your memory chips starts to degrade. So for those sort of things, we can make RTGs that can provide power for very, very, very long time. I'm talking about in thousands of years is doable. So suffice to say, if longevity is your longevity is your core goal, this provides the best amount of guarantee that you're going to have power at the end of your journey. Then it is location independent, as in it does not care whether you put it near Pluto or you put it on Mars, where the storms flat out block out entire sun for months. It is 100% location independent. It does not care. Like you can bury it underground, it will not care. You can send it outside of our solar system, it will not care. It's 100% location independent. But it does come with a cost. The cost is it's a very low controllable power output. Basically, it's like a heating element that is giving you power, let's say it's giving you 10 watts of electrical power, it's gonna give you 10 watts of electrical power 24/7 until its life expectancy. Of course, it's gonna lose 1% of power per year. So let's say you made 100 watt, in 100 years, of course, you're gonna go down to zero. But for practical reasons, you can't control it. You can't, like, of course you can waste the power, like you can simply not connect the RTG to any load, but again, you are wasting it. It's not like a nuclear reactor where you using control rod, you can conserve the fuel and spend it later on. You can't do that. For this reason, all the RTG system that we have right now in use, specifically with this, they also come with a very large battery bank, like lithium ion battery bank, which is gonna charge 24/7. And then when you have high load, basically this laser is quite high power laser, so it requires a lot of energy which RTG is not gonna provide. So RTG is like trickle charging the battery. Once the battery is full charge, the laser can be used for, like, let's say 1 to 2 hours. So RTGs does have this consequence. This is the most long-lasting and reliable power source we know about. Only consequences that it's very low power. Yeah, so don't expect it to run your entire space station. However, it can act as a very good backup energy source where it can maintain the minimum requirement, as in, like, air filters or communication systems. So it does have some use even in a human space station, and it's very crucial for long exploration missions. I mean, like, this mission would not have been possible on anything other than this. So this is nuclear decay, basically using nuclear fusion, but it's a natural decay of the materials is going to power this. So why not directly use nuclear reactor? So this is our final option. Now this has the advantage of being location independent. It does not care where it is. Awesome. And it has the largest power density. It can even exceed solar power. Now, of course, be mindful, if you go very close to the sun, as in, like, you could go close enough as in Mercury's orbit, yeah, then nuclear power plants starts to fade out in power because you can't compete against sun. But if you are far off, like let's say in Earth orbit or Moon orbit or Mars orbit or anything further than that, solar does not even stand a chance. So at those kind of distances, or let's say even in Earth orbit, but if you want to make sure you have, like, lot of power, I'm talking 10 to 20 to even 100 megawatts of power, this is the only option we have available. So we have location independence, it has a lot of raw power, but it does come with a consequence that it might actually blow up. RTGs are not dangerous. We know how to make RTGs. We know how long they last. Heck, you can have RTGs in front of your ship. Like, let's say your ship is traveling very fast. You can just put RTG in front and it's going to absorb a lot of incoming radiation. You might be like, isn't this itself radioactive? Yeah, but it's not cosmic radiation. It can absorb cosmic radiation. So there are some very interesting concepts where RTG itself is used as a armor. So, but this is very crucial. Now, this reactor that I'm showing you here is NASA's Kilopower reactor. Basically, it's a Stirling-based nuclear reactor. Now, it's supposed to last for roughly 10 years. Be mindful, this runs on Stirling engine, so this does give you AC power. Now, and it's supposed to last 10 years, not because the reactor itself will break down, but because the Stirling engine that is converting the heat into electricity, that will break down over time. So 10 years is their target. Of course, this is gonna run longer than that, but they can guarantee it for 10 years. And as I mentioned in my first video, few seconds ago, like, Soviet Union actually put a full-fledged nuclear reactor in one of their spy satellites. And suffice to say, this is one of the most reliable power source that we have, but we never actually used it because of the risk that it can blow up. Like RTGs, you can just put it and forget about it, but this you have to actively monitor, because if anything goes wrong, not only it's gonna produce radioactive waste, it's gonna actually detonate the whole thing. The radiation is not a big issue if you are on Mars, because Mars itself is very radioactive, as in, like, a lot of cosmic radiation is falling into the atmosphere. A lot of lack thereof atmosphere is also making sure that you get the radiation. Ultraviolet is also harming you. Basically everything is directly reaching you, so radiation from these things are not a concern at that point. However, if it blows up, then of course. So these are the 4 options that we have for power in space. So this was my presentation on Future Friday and about space power. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, I'm sorry, dislike it. And I would say leave a comment what you want to see in the next episode of Future Friday. Now, if you have actually watched it this far, come on, just subscribe. Just subscribe. I need 1,000 subscribers, man. Come on, just do it. Just do it. You don't need to press the bell icon. Just subscribe. Come on, you can do this. And anyway, as you watched my video, and I'm very grateful for it. Grateful for it. Thank you.